Wait for 2 days. Hello. 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 Already actually. It's not connected. It connects, but it's not something as much as I want. But yes, it's not simple. Video share नहीं है. Video camera turn. Yes. Including when we take it
Hello. Hello.
So I'm introducing Professor Pabitra Mitra. Professor Pabitra Mitra is a professor of computer science and engineering in IIT Kharagpur. He did his PhD from Indian Statistical Institute of Calcutta and BTech from IIT Kharagpur. He has been an assistant professor at IIT Kanpur and scientist at Center for AI and Robotics, Bangalore. He received the INAI Young Engineer Award, IBM, and Yahoo Faculty Awards. He has co-authored a book and about 100 research papers in pattern recognition and machine learning. Today, he is going to give a lecture on introduction to machine learning.
Thank you. Thank you. Online, am I audible? Yeah, I think I'm audible. Okay. So what I will do today is that provide you an introduction to the topic of machine learning, because one of the most important workload that we have in high performance computing nowadays are the machine learning algorithm. And there are a lot of optimizations in HPC, not just in software, even in hardware, which basically is made so that you can run the machine learning codes efficiently. So use of machine learning in HPC is two-way. First of all, there are many problems in science and engineering where you can use machine learning to accelerate the process of simulation or other methods. So you typically use a mix of machine learning, which is sometimes called data-driven method, and simulation techniques and numerical solutions. The other direction, so this is one direction. The other direction is that you can use the machine learning itself. Itself can be accelerated using GPUs and things. So there are typical strategies. There are some machine learning algorithms which are accelerated. So there is a very important direction of research called accelerated machine learning, which basically talks about ways to modify the standard machine learning algorithm, ways to develop code which can run these algorithms very fast. And the thing is that before, in fact, there are entire platform and toolboxes like the NVIDIA Rapid Framework and other frameworks, which are just a collection of tools which help to accelerate machine learning. So some of these tools we will be doing in the second half of today's talk by NVIDIA. My plan is to give you an introduction to the machine learning algorithms, such that when we discuss the accelerated algorithms, you know what is what. And nevertheless, these basic algorithms will help you in other applications. For example, besides numerical technique, that data-driven machine learning techniques, and together they would help you better solve a science or engineering problem. So I will start, and I'd like to keep it interactive. So any time in between, if you have a problem, you can tell me. And one more thing I'd like to tell you is that you can understand that machine learning is a huge, big topic. So definitely in these 2 hours, I won't be able to cover everything. But rather what I want to do is to go deeper into 1 or 2 algorithms and then give an overall idea of the of all more or less the main classes of algorithms. Okay. So before going into exact, I think many of you are already familiar with machine learning. Most of you are, in fact, maybe all of you are already familiar with machine learning. So this is just kind of a refresher. This is a refresher and maybe deeper into some of the topics. Okay, so basically the idea of machine learning is the second statement, the definition of machine learning, according to Tom Mitchell, who has a very popular textbook in machine learning. So a computer program is said to learn from experience E on some task T, according to some performance measure P, if its performance in task T as measured by P improves with experience. So the idea was that you develop algorithms which are not kind of static, which once you write and forget, not like that. But as you solve more and more problem, the algorithm would improve the performance. So there are 3 important things to be noted in this regard. Is that first of all, there is a role of experience, which sometimes we call training. Secondly, there is a role of adaptation, which we call as a learning. And the third, which is perhaps the most important aspect, is that so the algorithm is expected that it will not only perform well on the experience it has already seen, but also perform well on the new tasks or new scenarios. Okay, so this is what is known as generalization. So the any machine learning algorithm is said to learn only when it can generalize. Otherwise, a table lookup is enough. So the goal of any machine learning algorithm is that it should generalize beyond the experience it has already encountered. All right. So as you can already guess, the important part from an algorithm design perspective is kind of you can think of it as a system which takes some experience and converts it into generalization capabilities, and you have adaptation in between in the process. So any machine learning algorithm would basically involve how this adaptation happens. So we'll discuss them, and then. So now the question is why all this improvement, adoption, why all these important things are there. The thing is that people found that standard static algorithms, which computer science almost always uses, as well as many of classical artificial intelligence, like say playing a chess or something, which is based on standard topical, which don't have adaptation capability, they are inadequate for certain situations. For example, they are inadequate in a situation where we don't have complete information about the system, a very large scale system, say weather simulation or something. You don't have a complete information. I want to predict how much it will rain tomorrow from today's information. The problem is that I don't have the entire information ready. Second is often you have a dynamic environment. The environment would change with time. So naturally a static algorithm wouldn't work. It evolves with time. Okay. And perhaps the most important reason which initially led to the development of machine learning is that as you go into real life big problem, it's extremely difficult to write programs. See, any program basically articulates some knowledge about the system. Any computer program you write, whatever the human being has knowledge about solution of the problem, she will encode it in the form of a program. So for extremely large systems, articulating this knowledge as a program becomes impossible. So you can write a program to sort an array, but if I ask you to write a program to diagnose a disease or something, the problem is far too complex to articulate all the human knowledge that goes into this. So naturally, people drop this effort for really large problem where you want to write a program and do it. Instead, people said that learn by example, learn from a teacher. Learn from a teacher. Okay. So when you are learning to drive a car, the instructor wouldn't exactly tell you in this situation put this much of brake or turn the steering. It is impossible to describe every situation like that. Instead, what you do, so she will tell you that this is how you should drive. This is the broad direction, and you will learn from that examples. So that is what is done typically in. Okay, so how do we learn from example? So what people did was that they borrowed a lot of existing concepts from a lot of fields. As I say, data mining, control theory, statistics, information theory, evolutionary models, neuroscience, psychological models, cognitive science models, decision theory, a lot of decision theory. So many of these fields, they actually had rudimentary algorithms which would do such adaptation. And what machine learning did was they bring together all this into the form of an integrated theory. Okay, so as the theory of machine learning developed, depending on what kind of experience you are having, which meaning what kind of teacher you are having, who is giving you the experience, there are three different type of learning scenarios that can happen. The first is what is called supervised learning. That means your experience consists of a set of inputs, a set of possible situations, and the teacher along with that tells you what is the action in that situation, what is the correct answer. Okay, so the teacher will give you a question on which a student should practice. Also, the teacher will give you the correct answer to the question. Both would be given. Okay, so if you practice in such a situation, you have what is called a supervised learning environment. Okay, so this is the best because most of the learning happens when you have a teacher, but sometimes this is it is difficult also because it's difficult to have a teacher for everything. It's costly actually to have a teacher for everything. Okay, so there are two problems which fall in this category. One is called a classification problem. And the classification problem, maybe I'll explain this. Another is the regression problem. I'll explain this in detail. The second category is unsupervised learning, meaning the teacher gives you the question but doesn't give you the answer. So you as if practice the questions, you explore the inputs given to you, and then find out patterns in the question. Nobody tells you this is the right answer to this question. Nobody tells you that. Okay, you are given some input, you find out, you explore. That is why sometimes it's called exploratory learning also. You explore and find out patterns. And then what are the patterns we are looking for? Typically, we look for clusters in the input. These are the similar. For example, when you are driving, you will feel that, okay, all these experiences are when somebody is trying to cross the road or you are trying to overtake. These are all similar behavior. So that is a cluster. And alternately, you can have an anomaly. That means you find that this is something which stands out, which is a odd thing that is happening. Okay, that is also part of unsupervised learning. And finally, we have something in between, which is called reinforcement learning. So what happens in reinforcement learning is there is a teacher, but teacher doesn't tell you the exact correct answer. So the teacher allows you to explore and take actions, and depending on your action is good or bad, the teacher gives a reward or a penalty. So this is typically when we drive, let's say you have a driving instructor, the driving instructor wouldn't exactly tell you that that you have to put this much brake or turn this much steering. Alternately, what she will do is that you do something, she will allow you to drive. If you make a mistake, she will tell you, no, this is not correct, or this is the right thing to do. So that is called reinforcement learning. Okay, so okay, any question? Yeah, please.
The first supervised learning, reinforcement learning, sir.
Huh.
Is the data set is run before it is deployed in supervised learning.
The data set is available before it is
It
deployed.
is trained before it is deployed.
Deployed.
But in reinforcement,
It is continuously
it
learning.
is continuously learning in deployment.
Yeah, so there is no separate deployment and so reinforcement learning, it is on the fly learning. That means it is deployed. You do some, of course, you do some initial training before actually you put it in. And once it is put in, it is also sometimes called a lifeline learning or things like that.
When it is what?
It is still learning. It is still in the process of learning. Okay, of course, I mean, some practical scenarios, I mean, maybe for systems requirement, when you are confident that this is in job learning is over, then you stop it. But in principle, it can go on forever. That one advantage of that is that if you have an evolving scenario, if you have a dynamic scenario, reinforcement learning would still work. No, this is slightly different because instead of the correct answer, correct output, you have an reward function which tells how good your output is, not directly the output. Because what happens is in some scenarios, see, initially we said why did standard learning fail? Standard artificial intelligence fail because you have to write a program for every scenario, which is impossible for all. Then we said that instead of that, we'll give you examples. In this scenario, do this. In this scenario, do this. Okay, like your teacher or parent will tell you. Sometimes for very complex problem, even that is not possible because you have not. Nobody tells you in this situation do this because you have not seen that scenario before. So instead of saying, so I don't know if I should say it. See, when a child is very young, the parent would tell him or her that, okay, this is a cow, this is a bird, and things like that. It will exactly tell you the answer. But after some time, when the child grows up, the parent wouldn't tell you this is exactly what you should do. Maybe after school, parent will tell you study this, study that, study this. After some time, the parent will not tell exactly what to do. Instead, it will give the freedom to the child, and depending on the child is good or bad, the parent will give a feedback. You are on the right track or things like that. Because then the parent herself or himself doesn't know the answer, what exactly the student should. But as a broad idea, this is good or bad. So that is the situation. Okay, so let us discuss a little bit of these particular tasks in each of the scenarios. Okay, so first let us have the regression task. Regression task again is supervised learning. That means the training set consists of some input and the correct output for that input. Correct output for that input. So now, so if this correct output is a real number, a floating point number, then we call it as a regression problem. So input can be anything, floating point number or whatever. If the output is also a floating point number, then we call it a regression problem. Typical example, if I want to predict the rainfall in centimeters in the month of November in say Kerala. So that is a regression problem. You want to predict the stock price tomorrow. Okay, assuming it's a floating point number, it's a regression problem. Okay, so there are many examples. So for example, this is one problem we solved, which is a regression problem. So this is typically a cyclone. It typically maybe even now there is a cyclone getting formed in the Indian Bay of Bengal, and this cyclone moves land towards the land with time. And it is a regression problem to predict after 5 days where exactly the cyclone will be located. Or rather, the slightly defined problem is when exactly the landfall will happen, which location exactly the landfall will happen. And this has tremendous implication. For example, if you remember, maybe you are not even born at that time. So when super cyclone 2000 was there, a lot of people lost lives. Tsunami. Huge number of people lost lives in the eastern coast of India. But now you don't hear of any loss of life because the regression problem can be solved at least 3 days in advance. So everybody is relocated from there, moved from there. So, and nowadays you have exact within 10-kilometer precision where the landfall will happen. The only reason, so in IIT Kharagpur, we have been doing a lot of work. Again, this is an example where you are using the Paramshakti high performance computing as well as machine learning. So groups here in ocean engineering department who are working on that, Prof. Bhaskaran and others. So you can exactly use both of these to predict where the landfall will happen with a very high precision. Okay, I'll mention the other one. So this is when the output is real value. Instead, if the output is a discrete value, okay, number of possible discrete value, then we would call it a classification. Because each of these discrete values can be thought of as a class. Typical example, maybe I want to so let's take the rainfall, whether it will rain tomorrow or not. This is a classification problem. How much it will rain tomorrow is a regression problem. So classification problems are also very common. For example, image recognition or handwriting recognition. Okay, if you are doing a handwriting, it is one of these A to Z characters or 0 to 9 numerals. So you have 26 plus 10, 36 different classes. Given an input image of a handwriting, you have to put it in one of these classes. Okay, so I'll come to regression. Before that, quickly come to classification. Before that, quickly talk about the simplest machine. So one of the view of regression, one of the view of machine learning that arises while solving the regression problem, that it is a function fitting problem. It's a function fitting problem. So why I call it a function fitting problem? So if in the x-axis I write my inputs, I plot my inputs, and the output in the y-axis. So for every x1, I have a desired output y1. x2, I have a desired output y2. Okay, x3, I have a desired output y. So now this can be anything. Okay, x can be anything. X can be a vector also. I'm plotting in one dimension. And now for another x4, I want to find the value of where y is and to find locate value. So the way I would do in regression is that I will try to fit a curve with y1, y2, y3, and so on. And once I have done with fitting this curve, I will, for a value of x4, read off the value of y4 from this curve. And read values, read off the value of y4. Okay. All right. And that is my prediction about y. So for my existing training set point, I will fit a curve. I'll fit a curve and use that curve for an unknown input x to find out the y value. Now, this curve can be anything. This curve can be anything. Of course, the simplest thing you start up with is this curve is a straight line. This is a curve is a straight line. I think all of you have done this when you do the voltage versus current Ohm's law experiment in your physics lab. You plot a bunch of I values and a bunch of V values. You try to fit a straight line to V versus I. It is actually never a straight line. We have actually done the experiments because of the instrumental errors and other. In fact, there is no Ohm's law in reality. It's just an approximation. So if you plot it, you get a bunch of points. But instead of treating every point, you fit a line to this point. So the simplest, as I said, is a straight line. As you can, so now this x instead of 1x, it can be a vector. Can be a vector. Say I'll make a mistake on my notation. Maybe the vector can have axes x1, x2, x3, and so on. So what the linear regression would look like is that you have your y. I try to avoid the board as much as possible for the online people. So you can have okay. So this is the weight for the component 1, weight for component 2, all this added up and plus and bias term. This is the typical regression line. This represents a line or a plane or whatever you call it in hypertensor. Okay, so if I want to, so learning here, learning this scenario for linear regression, which is one of the simplest learning that has been done, and this has been done since the times of the mathematician course for a long time, is that is the method of least squares. The method of least squares. What the method of least squares say is that, so if you have some points and you want to fit a line to it, so all you do is that even the actual training points, you find out, you assume a line W1 x1 plus W2 x2 and so on plus W0. You assume a line and then find out the error. Find out the error, which is nothing but if you drop a perpendicular from the point to this.
Can be that closer. Can be closer. Can be that closer.
What a focus?
Actually, clarity is not.
Okay. Maybe I should use a. Okay. So what we'll do, how to find the error? What you do, you drop perpendicular from the point, the line, take the difference, and then you call the error. So now this difference can be either positive or negative, depending on the point is above the line or below the line. So what you do instead is that you take the square of this difference, right, which will make everything positive. Add them all. Right. So that would give what is called a sum squared error. And if you take the mean sum squared error, meaning if you have capital N point, if you have the sum squared error divided by capital N, you have the mean sum squared error, MSE. So now you can see that given every W1, W2, W0, given every line, particular sum squared line. So what you do, maybe I'll come back. I'll come back. This is the side. I'm sorry to know what.
Okay, okay,
I'll come down.
okay, that is fine.
This is surely not what. Okay, so what you want to do is that find out, solve an optimization problem, which will give you a value of W1, W2, W0, which corresponds to the smallest sum squared error or mean squared error. Smallest mean squared error. So this is the learning in this case is just an optimization problem. It's just an optimization problem where learning in this case is just an optimization problem where what you do is that for this particular, so theta, I denote theta as the set W1, W2, W0, and so on. So find out the value of W1, W0, and W2, which would minimize the sum squared error for all the given data points. Okay, so very simple. So this is a typical situation where most machine learning algorithm is actually an optimization algorithm. So how is the optimization algorithm formed? You have an error value. Okay, given certain parameters of the model. In this case, the parameters of the model are the slope of the line, bias of the line, W1, W0, and so on. Given certain parameters of the model, you find an error of the model. In this case, it's the sum square error. Okay, then over the space of all possible parameters, all possible models, you would call this line, you would call it as a model, a linear model. You find out the one with the lowest error. So this error is sometimes in machine learning terminology called the loss function or the cost function or the error function. Different names are there, and the space of all parameters are called the parameter space. And the optimization problem is to minimize by varying your parameters to obtain the smallest value of the error or the loss. This is the simplest example. In this case, this optimization problem is so easy that you can just take the derivative of the error with respect to W1, W0, and equate it to 0 for the minima, and then find out the values of W1, W2. In fact, the answer is very simple. There is some derivation. I'm just skipping it for in the interest of time. So if you do it, you will get the equation for W1, W0, which is the best thing. Yeah, please.
So in the error estimation, the data points are there, but we need regression fitting line to determine the error.
Right.
So how will we initially determine the regression line, which regression line to use?
Okay, so in this case, so when you are saying initializing, you are implying an iterative problem, iterative algorithm. No, in this case, as it turns out, this problem is so simple, you don't even need iteration. You have a closed form solution. Okay, so you define your, so see, think of it this way. Your cost or error is theta, your cost or error is theta. Theta is W1, W2, and so on, is a function of theta. You change your theta, your error changes. Okay, but this function is so simple. All I need to do is take the partial derivative of s theta with respect to W1, with respect to W2, with respect to W3, with respect to W0, and equate it to 0. Equate it to 0. Right. If we equate it to 0, and then you can find an expression for W1, W2, W0, all those things. Okay. So in this case, what you are saying is very much correct. In this case, I don't need an iteration. But when your error function is more complex, when your parameters are more complex, you cannot have such a closed form solution. It's impossible to have such a closed form solution. Okay. There, we start with a random initial value of these parameters. Any arbitrary initial value of these parameters. And then I think all of you have studied what is called a Newton-Raphson method. So you find out the minima of a function, you start with a random point, follow the slope, see where it interacts, follow the slope, see where it interacts, and so on. So this method, since you are following the slope and going down, it's called a gradient descent technique. You follow the gradient is the slope. You follow a gradient descent. So the problem is very simple. I'll try to explain the problem in simple terms. So suppose you are in a mountain. You are in a terrain, up and down and up and down. You want to go to the lowest point of the mountain, but you don't have a map of the mountain. You are in certain position. You don't have a map of the mountain. Okay, and you don't, since you don't have a map, you don't know which path to follow and go to the bottom of the mountain. So what you do is very simple. You look around 360 degrees, see which direction the slope is the steepest downwards. Slope is the steepest downwards. You take a step in that direction, maybe 1 meter, 2 meter, 10 meter. Take a step and move around that direction. Okay. Once in this new position, again look around. Again see which is the steepest descent direction. Okay, again step by step. If your mountain is well behaved, okay, this mountain is well behaved, human beings are well behaved, mountain, okay, but there if you look at the mountain as a function, as a cost function, if the cost function has certain properties, then this process is guaranteed to take you to the bottom of the mountain, at least near the bottom of the mountain. Okay, so this methodology is called a gradient descent. This is basically an extension of the Newton-Raphson numerical method technique. Okay.
If the set of data points are at a level like it refers any decimal function which would be like some step function like area state linear, area state linear.
Yeah, so yeah, very good. So no. So what you are talking about is a piecewise linear function. This will not work. So that you can see the example. Even for piecewise linear or slightly non-linear, say quadratic, not even piecewise linear, then this closed form expression doesn't exist. You don't have only for this linear, you have a simple closed form expression. Non-linear regression, don't have a closed form expression. You have to do a gradient descent. So gradient descent, what it is? Basically, we are solving an optimization problem. Over the all possible parameter values, I am trying to find a parameter value which will give me the smallest error. This optimization problem I am solving. In this case, the problem is so simple, a closed form solution exists. Otherwise, you have to follow an iterative technique, where a gradient descent technique, where you are just following the local neighborhood to find out the steepest descent and going down and down and down. So that is what I'm. Okay, I'll explain all this in more formal way. I just, as an intuition, I wanted to discuss it. Okay. Okay, so this derivation I'm not going through. This derivation I'm not going through. So, but this is the final expression. This is the final expression. So if X is a vector consisting of all the inputs stacked one after the other, and X prime is the transpose. So the final weight vector, the parameters W1, W0, we call it weight sometimes. Weight vector is X transpose times the Y vector, which is the output vector, divided by X transpose X vector. This is the standard. So basically, it is the covariance of X and Y variables divided by the variance square of the X. I think most of you who know regression knows about this formula. It's the regression formula. But you can derive it by minimizing the squared error function. Okay. But moment you have more complex error functions, moment you have more nonlinear functions, this methodology does not work. You have to have a iterative gradient descent technique. And all the GPU accelerations, everything that you are talking of in the deep learning concept and everything is basically finding, doing hardware or compiler optimizations or software, which will help you solve this Newton-Raphson gradient descent problem in a faster way. So all of HPC is directed towards solving this optimization problem first. Okay. So neural networks are also can be thought of regression, but with a very complex, sometimes called a universal approximator. So I don't know, any of you, if you have studied engineering drawing, you used to use something called a French curve. Any curve, you can use a French curve to fit it. So it's kind of a universal approximator. So neural networks are universal approximator. It's a regression problem, but extremely complex, extremely rich. It has all kind of curves that the parameters can adapt and realize. But the way you find out the neural network weights is by this gradient descent technique. And all of, as I said, all of this GPU acceleration and everything, basically, and this takes time. This is an iterative technique. It takes a lot of time, because you can imagine that every step of the gradient descent, you have to find the error, which is the sound error of all the data points. If you have a large number of data points, you are finding the error for each and every data point, adding it, and then doing it again and again and again. So which is very time consuming. And we need accelerations for time. Okay. All right. So I think you have already pointed out that this doesn't hold everywhere. For the simple linear case, it holds. For other nonlinear case, such a simple technique is difficult. You need a nonlinear regression. You need nonlinear regression. And nonlinear regression, there is no general technique for nonlinear regression. There are something called kernel functions, kernel regression. We'll explain that slightly later. But you have to go for a nonlinear regression. Okay, there is another problem, which is, so what I'm trying to do is to trying to explain the problems that you have in general machine learning as manifested by this regression line fitting point or a curve fitting point of view. Okay, so one problem we already envisioned is that it's an optimized problem to solve, and you have to solve it iteratively. The second problem is that suppose I have solved this optimization problem, everything I've solved and got a curve. Okay, but suppose, let me take an example. Suppose my training data is something like this. And I have to assume what type of curve I fit. Is it a straight line or a quadratic or a cubic? Or so let's say it's straight line. Is it a good fit? Maybe it's too simple trying to fit. Is it a good fit? No, even not. See this dotted line, it exactly fitting or touching zero error for every input point. But definitely this is not a good fit. Why this is not a good fit? The generalization would be poor. Because maybe a human being, if you ask her to fit a curve, she will fit something like this or something like this. Or maybe she will fit something like this. Whereas definitely this curve, if I use, has good amount of error with what a human being would do. Why this error is there? Because it's too complex. I'm too closely trying to fit the input data. So this is sometimes called rote learning. If you just memorize your exercises, you can solve all your exercises without error. But in the exam hall, when an unseen question comes, you won't be able to answer. Okay, maybe this is something about right. This is something which is maybe the right thing to do. So can any of you tell, can I modify my optimization problem to ensure that I get a curve like this and not a curve like this? Because if we minimize the sum squared error, we will get this too complex curve. Here the sum squared error is very large. Here it is almost zero, but I don't want that. So maybe just optimization on the sum squared error itself is not exactly the right thing to do. You have to minimize the error, but that's not all. You also need to look at the generalization capability. You also need to look at the generalization capability. You need to look at how good my model is. So can anybody tell, can I modify my optimization problem to ensure it's not just the sum squared error I'm looking at, but also something else, so that I get a curve like this? Any idea what else can go into the first function?
Some error tolerance.
Yeah, that's actually called a margin. You can put error tolerance. Right. So yeah. So it's okay to make a little bit of error. You don't try to fit exactly. It's okay to make a little bit of error, but not too much of error. That is not. That's called the.
We have to optimize.
That you have to optimize.
Tolerance.
Tolerance you have to optimize. Very good. This is a notion of something called a margin. So that tolerance would be called a margin. Any other direction? Any other possibility?
Said outliers maybe that.
Right. Right. I don't try to fit the outliers. Okay. Yeah. So that actually should. So the margin can be modified. Instead of giving an exact margin, what I can say, I can give a probabilistic margin. I say that likelihood that it is inside the margin is very high. And if it is just one or two outlier point that do not contribute to the overall likelihood, so it's okay to ignore them. Most of the points on the average are in this margin. It's okay to ignore a few points because they do not contribute to the probability. They're individual small, 1 out of million points. Okay, so anything else? All these you have said so far are very valid concepts. These are used in deep learning everywhere. But these are very common sense, as you can see. So most of machine learning is actually using this common sense in a mathematical way. Anything else? Anything else? Yeah, in certain way. So another important thing is that, see, the number of coefficients that we need to describe a line is only two in one dimension. To describe this complex curve is maybe 100. Whereas this is maybe 3 or 4. This is a quadratic, maybe 3. So the number of parameters of the model should not be too less, should not be too high. If it is too less, we call it as underfitting. If it is too high, we call it as overfitting. So this line would be an underfit. This line would be an overfit. So instead, what you can do is that this is sometimes called a parsimony objective. Meaning parsimony is you spend less. You lead a minimal lifestyle. You only buy things which you absolutely know. You don't. It's not that you are totally without any belonging. You have the basic needs. Okay, whatever minimum food you need, you have everything, but don't overspend. This is called a parsimony principle. So there is a famous principle in machine learning called the Occam's razor principle. Okay, so the Occam was he was a philosopher, also a barber, and in England around maybe 16th century or so. So that time when you build a razor to save, he gave a principle. He encoded in this is like in India, you have many of the knowledge encoded as poems and such things. So he encoded is saying that when you are building a razor, build the razor enough so that it's good enough to save, but not more complicated than that. Then it will break down after some time. So he encoded it in this kind of allegory, and then that is the fundamental principle. So parsimony in this context is you have only as much parameters that is required to keep the error small, but not too many. So what you can do is that you have something called a sparse regression, meaning the number of non-zero parameters W1, W2, W0 that you have, that is also a member of the cost function that is added to the sum square error, and you minimize both these two together. So your error is not just the sum square error, is the sum square error plus the number of parameters you require to minimize, to fit the model. The summation of these two should be kept as small as possible. So this is the principle of sparse regression. So there are a lot of literature you will see on something called a sparse regression. So this is typically when human beings do a prediction. If you want to predict something, there are 100 different factors that this prediction depends on. But typically you would consider only say 5 or 6 of them, not all of them. For others, you ignore. This is a principle of sparsity. Okay, so all these methods that we talked about, that for tolerance and this sparsity and everything, yeah, these are called regularization techniques. Yeah.
Suppose I want to solve a PD, governing PD using Neural.
All right.
So then the means I am asking that whether the terminology can be same on sparse regression, because there also I am minimizing the risk.
Exactly.
But
So see, all these principles of overfitting, sparsity, regularization, optimization, cost of error optimization, I am explaining for regression. But as I told, these principles hold for any machine learning algorithm. So if you are doing a neural network based PDE solution, the same principles would hold there. Same principles would hold there. Okay, see, wow. Maybe I don't know I'm doing the right thing or not. Since we have only 2 hours time, I am just explaining 1 or 2 concrete algorithms and explaining the concepts around them. And how these concepts are applied to existing algorithm is a 1 semester course. Is a 1 semester course, how we are applying. Okay, so the best I can do in this situation, take 1 or 2 simple algorithms and explain these basic principles. And when each of you, when you pick up a basic or detailed algorithm, say a support vector machine or a neural network, then apply these principles here and study exactly how this principle, the details of the methodology. So that is what I'm trying to do. Okay. So next we move to classification. Next we move to classification. The problem here, as I said, is that the input is anything, a vector or a number or floating point number, categorical number, whatever. The output, instead of so if I talk of a function fitting point of view, the output is now not a real value. It's a discrete number, maybe binary number, 0. So how do I think of it? So now I have a different picture in my system. So again, let's take my input X, output Y. But now Y is discrete value. Okay. So say here the value of Y is this much, here the value of Y is this much, here again this much, and maybe here this much, and so on. Something like this. Instead of trying to fit a function like this, I will do what is that all the values of Y which are here, I call them as set 1 or class 1. So this is all the X belonging to set 1. This is all the X belonging to set 2. This is all the X, sorry, this is also set 1. I'll call it class 1. This is all the X belonging to class 2. This is all the X belonging to class 3. Okay, so now I have a membership query, meaning when I have an X, I see which set it belongs to. So I learn the set of all X for which output is Y1. The set for all X which output is Y1. So instead of trying to fit a function, I will try to identify these sets. I'll try to identify these sets. Okay. So if this classification problem has K such Y1, Y2 up to Yk, I will call it as a K class classification problem. If K equal to 2, I will call it a binary classification problem. If it is a binary classification problem, it is just a set belonging as an indicator function. Either the output is 1, X belongs to that class, or if output is 0, X do not belong to the class. For example, I am doing a credit card transaction. Whether the card will be a valid transaction or invalid. It is valid, output is 1, it belongs to the valid set. It is not valid, output is 0, it's outside. Yeah.
suppose on either side of the peak, we have 2 levels equal.
So the set is a union of all the values of X for which Y is set. It's a union of these values. If they need not be continuous. If they are continuous, we call them as a convex class. If they are not continuous, that's a property of this set. It will either be convex sets or not convex sets.
Suppose they are not continuous, and I want to apply the gradient descent principle on these sets.
Oh, it would not work. So typically, yeah, very good question. So in regression, the error functions that we have are nice. So gradient descent works when your error W versus error is W is nicely behaved. I think those of you who have implemented Newton-Raphson knows that Newton-Raphson works in these convex error functions on. Okay, maybe something like this is okay, more or less convex. It's okay. Somewhere close to the solution. But in a regression, typically the error function is convex. In classification, where you measure error by how many times the class, predicted class matches the actual class, that's not a convex. That's not a convex. That's a very nonlinear function. So how do I apply gradient descent in that situation? There are roundabouts. For example, you take the logarithm of the probabilities of belonging to this class as of predicted class as opposed to the actual class. Take the probabilities, take the likelihoods, take the likelihood ratio, take the log of the likelihood ratio. Then it becomes a nice convex function. Then you optimize. Or there is something called cross entropy and other kind of definitions which makes it convex. So we'll go into that. We'll go into that. But what you try to understand that it's a so both for regression. One more important point I want to touch upon, and then we'll take a short break, tea break, is that how do I know when learning is over? A student has finished learning or stopped learning. This is again typically what you do for a student in a classroom. Okay. So typically the problems that I give you to solve in a classroom, which you practice upon, these are called the training set. This is a set of data points, set of inputs, where you are practicing to improve yourself, to learn to improve yourself. It's called the training set. Then what happens is that sometimes inside the class, or maybe say you are preparing for the GATE exam or something, you take some mock tests. You take some mock tests, and depending on your mock test performance, you either study thermodynamics in more detail or study machine learning in more detail, things like that. Okay, so the purpose of this mock test is it will help whether whatever you have practiced on your practice problems, exercises at the end of the book, whether that is enough or not. Whether that is enough. So this mock test would be called validation sets. This set of training example would be called validation sets. Okay, so typically learning process happens. You use the training set to change the model, update the model, optimize. Then after some time, some rounds of update, you validate. If your validation performance is good, then you take the final test. And that is called a test set. That is the final exam. Once you have taken the final exam, for your lifelong, you are evaluated on the basis of that final exam. You get chance in a college based on that final exam and so on. So this final exam would be called a test set. So, so there are three important ways the learning is evaluated. One is you train on the train set, validate on the validation set, and test on the test set. The purpose of test set is to the performance of test set is the basis of comparison between multiple machine learning algorithms and picking up the best one. So that is the principle. So same principle you can apply to regression, to classification, to whatever. Only thing is that the performance measure, whether it's the sum squared error or the classification accuracy, that would depend on the task that we are solving. But the basic principle is the same. So what I will do is that I will, so this is a typical scenario. This is a typical scenario in a classification task. So you have a training set. Based on the training set, you learn a model. The model in this case is just the function that you are trying to fit. It's just a function that you are trying to fit, the mathematical function you are trying to fit. The learning algorithm would typically be consisting of an optimization problem, which will get you the best parameters. Once you have the model ready, you apply the model and validate on a test validation set and apply on a test set and predict on a test set whose output is unknown. Whose output is unknown. Then you say the model is deployed. The model is deployed. Okay. Now there are many intricacies of evaluation. If you just take one mock test and your performance is good, you may be fooled into believing that your preparation is good enough. So you take multiple mock tests and take the average. So these are training methods called statistical methods.
So we will be having a short break of around 15 to 20 minutes. 10 minutes, 10-15 minutes, a short break is there. Then we will start the session shortly.
You will from link with other people. Please fill it up.
Okay, so I will discuss one simple classification algorithm, which is a probabilistic algorithm. I will explain it with a simple example, and you will get the idea. But okay, so let us start with a simple binary classification problem. So what you have is that two type of fish are there. So what I will do, I will measure the length of a fish. I will measure the length of a fish and decide which type of fish it is. I'm considering two type of fish. So the left hand side is something called a hilsa. So you are in Bengal, so you have to hear about fish. Okay. So yeah, so the left hand side is perhaps the best, the fish Bengali like most. It does not include me, of course. It is a hilsa fish. It's a very costly fish. And the right hand side is a tuna fish. So I tried to impress upon you with this picture is that the tuna fish is much more longer than the hilsa fish. So the hilsa fish typically is about a feet long, and this is about a 4 feet long, typically. All right, so my job is as follows. What I will do is that I will measure some kind of robotic fishing or something. I will measure the length of the fish from the head to the tail, and based on the length, I will decide what type of fish it is. What type of fish? Right, and I will use a simple rule. I will decide a threshold length, say 1.5 feet or 2 feet or something. Any fish with a length less than equal to that length B, I will call it a hilsa. So very simple decision rule. Anything more than that, I will call it a tuna. And this B, I will call it as a boundary length. Anything below that is hilsa, greater than is tuna. The question is, what is a good choice of B? That is, how do you decide what is this threshold value? To do this threshold value, first thing I will do is that I will go to the market. I will measure the length of say 1000 hilsa fish and 1000 tuna fish. I'll measure their length so that I get an idea what is a good boundary length. Okay, I'll measure the length of this fish. And then using this length, I will compute some statistics. I'll explain what the statistics are. So what I will draw is I'll do is that in the x-axis, I will plot the length of the fish, and I will divide this length into small intervals. Small intervals meaning say from 0 feet to 0.1 feet, 0.1 to 0.2. Small intervals, I'll divide the length. And among these 1000 1000 fish of which I have measured the length. In the y-axis, I will plot how many of them as length in these small intervals. So for example, say 5 fish have length from 0 to 0.1. Say 10 fish have length between 0.1 to 0.2 and so on. I'll plot these vertical rectangles and I'll plot this. Okay. So this is some, as you can understand, this is sometimes called a histogram. This is sometimes called a histogram. So the x-axis is the length of the fish, which I have split it into small intervals. Y-axis is the count of the number of fish out of these 1000 fish, which has a length in each of this interval. Okay, so this I will do first for all the 1000 Hilsa fish and then for all the tuna fish. Right. So now if I hypothetically make this interval small enough, and in this 1000 instead of 1000, if it is 100,000, let's say, then this curve will look, so if we join the top of this histogram, it will be smoother and smoother and smoother. And instead of count, what I do is that I plot the relative count, meaning instead of exactly 5 fish, I'll plot 5 by 1000. Or instead of 10 fish, I'll plot 10 by 1000. The relative frequency I'll plot. So that is between 0 and 1. So if I do that, then this curve will become smooth and I will have what is called a probability distribution. It's called a histogram will convert to a probability distribution. Okay, what this distribution means, the top distribution, the green one, it means, for example, at a particular point, say length equal to 1.75 feet, the y-axis will give me what is the probability that a randomly picked up Hilsa fish will have a length of 1.75 feet. So how do I find that? I go to this green distribution. I go to 1.75 feet in x-axis. I read out the y-axis. So value between 0 and 1 is the relative count that I plotted. So it will give me the probability. So this similarly for tuna. So this is called a class conditional probability distribution. Why it is called a class conditional? Because it is a conditional probability. The top one would mean that given that the fish is Hilsa, what's the probability its length is 1.75 feet. And the bottom one is given that the fish is tuna, what's the probability its length is 4.25 feet. So these are the conditional distributions. Okay, and these two conditional distributions easily from these 1000 samples that I have taken, I can construct these distributions. Now I will use these distributions to find out the boundary such that in the left hand side it is Hilsa, right hand side is tuna. How do I find out the boundary? So let me plot them side by side. Let me plot these two distributions side by side, and let's say that this is my boundary. This is my boundary. So anything having less than b, I'll call Hilsa. Right of b, I'll call tuna. So what is the error? The classification error I'll get. I can get two type of classification error. One is the fish is actually Hilsa. My rule says it's tuna, and the other way around is the same type. So now let's see for how many fish, or rather what's the probability that of type 1 error. That means actually tuna classified as Hilsa. So that I will do this way. So what are the fish classified as Hilsa? So this much, this height plus this height, because remember the height was the number of fish that is in that range. Okay, so right of b, what actually Hilsa. So it's so many fish are, say b is 2 feet. So many Hilsa fish has 2.1 feet, 2.2 feet, 2.3 feet, 2.4 feet, and so on. Okay, so if you add them all up, this area is the total count of number of fish who are actually Hilsa. My rule says tuna. But I have taken probability, so this area will actually mean the probability that the fish is Hilsa, actually Hilsa, classified as tuna. Now let's take the type 2 error. That means any tuna fish whose length is less than 2 feet, I'll say Hilsa. So what's that error? So this many tuna fish are less than 2 feet, this many, this many, this many. So this area is the one which is type 2 error. So the total error probability is this plus this much area, this much area, right? I cannot draw here, but I think I hope. Yeah, I can draw. So this is the total area of both errors are into error, right? So now you can see that oh no. Now you can see that if you change your position, how do I erase this? Just a minute. Okay, so if I change this, if I change my position of the B, the error will change. For example, if I place my B here, the error amount will be different. Now I ask you the question, where should I place my B to get the minimum error? Where should I place my B to get the minimum error? At the intersection. Very easy to see that. Very easy to see that, because if we place it at the intersection, what is the error? This plus this, that is the error. Anywhere else you place, it is this plus this much extra. Anywhere else you place, it is that much is always there, plus something is added. Right. So the smallest error is when you place the boundary, I call it B star, at the intersection. So what is this intersection? This intersection is the length at which the probability of being a Hilsa is same as the probability of being a tuna. Because see, y-axis for the left-hand curve and the right-hand curve matches. That's the intersection. Okay, so y-axis is the conditional probability. So B star is exactly the length at which it is equiparable to be a Hilsa or a tuna. It is equiparable, and that should be the current B star. Right? Okay. Any question? Because that will give me the minimum error. Yeah.
Instead of shifting it to the intersection point, the threshold value, can we compress the Bayesian distribution curve so that it gets the area?
No, curves you cannot compress, because those are obtained from the statistics I have got for Hilsa fish. So that's a property of the Hilsa fish. That's a property of the
normalization or something.
No. What about normalization? The shape. Okay, normalization, the curve will go up or down, but the shape of the curve, the intersection will remain the same. Shape of the curve will not change. You can magnify both the curves or bring down both the curves, but you cannot change the shape of the curve. That depends on the how Hilsa is created. Okay, so all right. So this is the optimal decision boundary. This is the optimal decision boundary. So what I have done, I have successfully obtained this decision boundary in a very simple way. I measured the population of Hilsa and tuna fish. I constructed the class conditional distributions. I found out the intersection, and that I call as my decision boundary. Okay. So far so good, but there's a slight problem to this. So it depends on where I am trying to find out taking this decision. If I am taking this decision in Calcutta, maybe, then anyway tuna is not available in a market in Calcutta. So even if we have a very small, a very large space, maybe it's still a Hilsa, because there is no tuna at all in Calcutta. Similarly, if I am doing the experiment in, say, California, so then even a small, there is no Hilsa in California. I don't know it's true or not, but okay. But in most of the fish is tuna. So even though you find a very small fish and this rule says that it should be classified as a Hilsa, maybe you should not do that because there is no Hilsa in California. Okay, so these factors you have to take into account. Okay, so how do you take into account this factor? You take into account this factor by something known as a prior probability. Prior probability means if you close your eyes and go to the market, and if you close your eyes and go to the market and randomly pick up a fish, what is the probability it sells up? And similarly, yeah, what is and maybe what is the probability? So so this is This is prior, meaning that you know these probabilities before even measuring the length of the fish. Before even measuring, knowing some, before even looking at the fish and knowing its length. Okay, this is a prior. This is a property of the location, or the time, or the environment, or whatever. So this would be called a prior probability, and this is independent of a particular individual fish length. This is a overall global property. So I will call this as the prior probability. Okay, so now this prior probability will depend on the environment while you are doing the experiment. Okay, so definitely this prior probability should be a factor also in your decision. It's not just the boundary length left or right. It's also this prior probability. You have to. It's not just the class conditional probability. It's also the prior probability that you need to look into. How do I look into? So what Bayes suggests? What Bayesian people suggest, not Bayes. Bayesian is actually a school of probability. Many people are either Bayesian, probability people are either Bayesian or non-parametric. Anyway, so what he says, they say, is that Bayes says is that you just multiply these two probabilities. So this curve that you have, you multiply the green curve by the prior probability of Hilsa, multiply the pink curve by the prior probability of Tuna, and then take the intersection. So if we are in California, where the prior probability of Hilsa is less, then this green curve will come down, and the pink curve will go up. So the intersection will shift to the right. Yeah, to the right. Okay, meaning even very small fish would still be called a Tuna. Intersection will shift to the left, right, left, yeah, left, right. Intersection should move to the left. So the boundary is no longer 2 feet, even 1 feet we still call it Tuna. And the other way around. So if you are in Calcutta, this green curve would go up and the pink curve would go down. The intersection is shift to the right. So even a 4 feet fish, no, not 4 feet, maybe 3 feet fish would still be called a Hilsa. Okay, so you should take the product of these two probabilities. The thing about Bayes is that, in fact, I'll just tell you a bit of history. This rule of combining these probabilities were proposed by Bayes even before probability was formally defined. This is a general principle. And in fact, probability is defined this way, that you can multiply two things and still get a probability, is because Bayes wanted to multiply these two things instead of adding them. And many of the axioms of probability, the rules of probability, they had to comply with this Bayes theory. And that's why it became defined that way. Kolmogorov defined it that way, so that they can still multiply things instead of adding things. So if you have in any decision making, you have two factors in decision making. Either you can add them or you can multiply them. So Bayes decided you should multiply them in this situation. And many of the probability theory is defined that way. So in this situation, they should be multiplied. The laws of probability are defined that way. The laws of probability came later than Bayes. Okay. All right. So these are the things you should multiply. And in fact, it turns out that if you divide it by one other probability, which is sometimes called the evidence probability, which is if you randomly pick up a fish, irrespective it's Hilsa or Tuna, what's the probability its length is 2 feet? This is sometimes the data probability, or sometimes called the evidence probability. If you divide by this times this by this quantity, by applying the Bayes rule of probability, you get this quantity. So Bayes rule of probability is P A given B times PB is P of B given A times PA. So if you substitute A and B accordingly, so this product divided by this gives this. But see, the denominator here is independent of whether it's Hilsa or Tuna. So it's kind of a constant. Yeah.
Essentially, our base model here it's imposing additional constraints of this location.
Right, exactly.
So now my question is, why don't you also add a constant of time, whether it's a high tide or low?
So the idea is that all this time, space, everything is together encapsulated in the prior probability. So the prior probability encode. So that's the beauty of this Bayesian approach. All you know about the problem. So you are solving a chemistry problem, any domain knowledge you have. Any domain. So suppose I solve the problem. There is something in chemistry called a perovskite, organic perovskite, which are material which absorb electricity, absorb sunlight and produce electricity, and so on. So we wanted to predict whether some chemical compound will have that property or not. Yes or no? Based on certain bonds and other factors and hydrophilic and all this kind of thing. Okay, so all the knowledge of chemistry, like similar molecules behave similarly, or if this molecule is there, everything together is aggregated inside this prior probability. It's the prior knowledge. Everything. So that's the beauty. All your prior knowledge, the probability theory says you just have a number, one single number. Okay. So that thing makes things very simple. Okay, so the left hand side becomes is denoted by something called a posteriori probability, the product of these two. Note that even if we ignore the denominator and just look at the proportionality, that prior times class conditional, which is sometimes called the improper posterior, if we drop the denominator. If we take the posterior probability or dropping the denominator, still the intersection point does not change. The intersection point is independent. Even if you drop the denominator, the intersection point of the posterior would remain the same. So we don't bother to compute the denominator. We don't bother to compute the denominator. Right. Okay. So since this is the base rule, this is called a base classifier, and it can be shown that this classifier has the minimum error possible. So this is the theoretical lower limit to the error you can have. Any classifier can have. This is sometimes that's why called the optimal base classifier. And the error is called the base error. It's the theoretical lower limit. No, because of the nature of the data, no other classifier can make a lower error than this. It's the absolute lower limit.
In this model, if I take the area,
Right.
integration of y dx.
Right. It will be 1. It's a distribution.
So it's only the error.
Only the error, right?
And
Excellent. So that is sometimes something called a Bayesian model averaging. Is the expected error of all the models given a prior over the models. Okay.
Partially differentiate with
Yeah, it is possible. It is possible. But it's computation. In fact, I don't know. We'll make Makwana. I will discuss this in. This is called a Bayesian optimization. So when you are taking derivative with linear regression, it's a normal optimization. If you are taking in a derivation in a probabilistic setting, it's called Bayesian optimization. That's extremely. It is difficult to define a gradient descent for Bayesian optimization. Extremely time consuming. There are a lot of toolbox, Google TensorFlow, PyTorch, they have toolbox for this Bayesian optimization. Okay, so far so good. So I'll my final rule is I'll look at the posterior distribution, find out this intersection. One question that may arise in your mind is that okay, for 2 fish fine, but we have so many type of fish. What about a multi-class problem? What about a multi-class problem? Okay, so for this, you look that I'll do a shortcut, but I will not a shortcut actually. So what I will do, notice one thing, left of B star, the green curve is above the pink curve, and the right of B star, the pink curve is above the green curve. So I can reformulate by decision rule, my decision rule that left of B star is Hilsa, right of B star is Tuna. And actually explicitly finding B star, what I can do, for a given L, given length, I find the P Hilsa, the posterior for Hilsa. I find the posterior for Tuna. Whichever is higher among these two, I put it in that class. I classify it into that class. This is equivalent because you can see left hand P star, everything will be classified as Hilsa because Hilsa is above the Tuna curve. The right of B star, everything will be classified as Tuna because the pink is above the green curve. So this principle, because you are taking the higher of the two posterior probabilities, it's called the maximum a posteriori probability rule. Okay, it's equivalent to the B star intersection rule, but you don't need to compute B star. All you need to do is that given a L, compute this P Hilsa given L, compute P Tuna given L, compare these two, whichever is higher, whichever is maximum, classify it as that class. This is sometimes called a MAC rule. The good thing is that if you use the MAC rule, you can easily extend to multiple classes. Suppose I also have another fish called shark. So what I will do is that I will particular L, I will compute P Hilsa given that L, P Tuna given that L, and P shark given that L. I'll compare these three. Whichever is the highest, I'll classify the fish according to that class. So this is so I can easily extend to multiple classes. I am no longer I have thrown away that B star and all those concepts which I explained to you actually for the intuition. Actually, nobody computes B star. We'll just apply this man. Nobody computes B star. So B star is actually called a class boundary. Unless you are really interested, don't bother about the class boundary. Okay. So that I think does it. And what I want to tell you is that see this this is what is called a univariate problem, meaning I am measuring only a single parameter about the fish, just the length. I could have measured more parameters. I could have measured the weight of the fish as well, the color of the fish as well in some color scale or something. I could have done that. I could have done so then this distribution should become high dimensional distribution. So if I take two length and weight, it would become bivariate normals. And then instead of B star, these two normals would intersect along a curve, a decision boundary. Okay, instead of a single point. Okay, but the MAP rule still applies. So I can extend it to multiple attributes. So if you have a number of attributes A1, A2 up to AN, attributes varying length, weight, color, and so on, I can still apply the base classifier. I can still apply the base classifier. But the problem is, okay, this is an example. I'll skip this. So this is a multivariate problem. So I want to predict whether a species is a mammal or a non-mammal depending on certain attributes of the fish, a phylogenetic attribute of the fish. Okay, so all these are my training set, and this is the new species I have found. I want to classify whether it's a mammal or non-mammal. So I can use the same principles of estimating these probabilities for a multiple variate, and that is one problem which makes them simpler. If I assume that these attributes are independent of one another probabilistically, meaning if some or maybe say the color of a fish is independent of the length of the fish. It's a black or white. It's independent of the length of the fish. Okay, maybe weight is not independent. Weight depends on the length. Okay, so if every attribute is independent of one another, then this class conditional probability for multiple variate can be written as the product of the individual univariate class conditional probability of each variable. So probability of a fish having length 2 feet, weight 1 kilo, color silver, even it is Hilsa, is the product of a probability that the length is 2 feet given Hilsa, weight is 1 kilo given Hilsa, color is silver given Hilsa. It's the product of these two. If this is so, then this is called a so it is just the way you calculate your class conditional probability, either as a whole joint probability or product of what are called marginal probabilities. If you can do so, if you can factorize it out as individual products because of the independence, we call it a naive-based classifier. It's just a different method of computing which is allowed. Okay, so for naive-based is actually computationally very easy to calculate. Very easy to calculate. Sometimes there are partial independences which are captured by something called a Bayesian network instead of a naive-based classifier, but I will not go through that. Okay, so this summarizes the base topic of Bayesian classification. There are many other like decision tree, neural networks, support vector meshing. Today's second half we'll talk a little bit more about neural networks. And there is another thing that people do which is called a ensemble method. That means you take a neural network, you take a decision tree, you take a Bayes classifier, and you employ all of them, take their prediction, take the average prediction. This is basis of methods like random forest and boosting and things like that. We'll share the slides of all of them, and we'll do a hands-on on this in the afternoon in the next slide. If you want to find out more details about these methods, this is a very nice textbook, Tom Mitchell, and this is another slightly mathematical pattern classification by Ruta Hart and Strong. These are very good books. There are many more details which I'm skipping. Okay, so with this, I close. If there are any questions I can ask, you can ask. If there are questions, you can ask. So I'll share with you two more slides about the decision. Here, decision tree is there. You can go through that. And what I suggest is that you quickly go through them. In the second half, the NVIDIA people, they will do a complete tutorial how to implement the Bayes classifier and other classifiers in a GPU setting. How you can accelerate this probability computation and other things. Okay. So thank you.
Thank you very much, Mitra sir. And now we request Somnath sir to present the webinar.
Are there any questions in the? Okay.
This one is the.
There's what here.
We have yet another session, which will be taken by another esteemed speaker, Dr. Shan Bhattacharya. So allow me to introduce. She is an assistant professor in Department of CEC at IIT Kharagpur. She comes from a background of microarchitectural security and is generally interested in teaching and research of computer architecture, computer security, microarchitectural advancements, and their inherent security implications. Today, she'll be covering aspects of exploiting leakages in CPU and GPU microarchitecture. What is there is the mic.
Somebody spoke. There is somebody.
Okay. Give me phone. Huh? This is. একটু বাকি
Hello. Okay.
Oh, okay, okay.
Got shifted.
Okay.
Now is it better?
Fine.
You can hear me also properly. So first giving an introduction about myself. I'm Sharni Bhattacharya. I've recently joined in computer science department of Pabitra as an assistant professor, and I am
Slide the ears and then the microphone is stable. That is good. Yeah, that's good.
it's you. Now should it?
Yeah, it is good. Okay.
I work in computer architecture security. So in that context, I might be asking some questions initially to understand where should I start from, right? So are all of you familiar about computer architecture, or do you have a background of computer science in some way or the other? Do you understand like how a program is mapped into the computer architecture components, how it uses different part of the computer system to perform certain computation? Is it okay with you, right? So I will start from that basics and slowly work on top of that on computer security. So the thing is like we have been in my PhD, I have been working on microarchitectural security to just understand what the term means. It typically says that, okay, given a computer microarchitecture, like given a computer architecture as a whole, looking at the particular processor generation and looking at the particular vendor from where it is coming. By vendor, I am trying to that, okay, if it is an Intel microprocessor, or is it an AMD processor, or is it like an NVIDIA microprocessor? So every vendor has their typical way of dealing this computer architecture blocks in a certain way so that it performs in a certain way according to their benchmarks. Okay, so the internals of those particular computer architecture blocks, like how you actually place them, what are the sizes of those components, and how you would like to optimize it for certain applications. This is particularly what we call as microarchitecture, right? The fun part comes the computer architecture and microarchitecture has been in as intuition and in as silicon chips have been over like 40 years like in market, right? We see it in various forms. We see it in our mobile devices, we see it in our systems and everything. But the connectivity, the internet connectivity of those devices have gone up so much in the last 10 years, right? Now we don't even do computations on our systems anymore. We do computations on the cloud. So the problem now comes into picture that if you are constantly connecting to the server for some amount of computation, getting it back, there is a basic, very strong encryption protocols that are running in background, which is kind of invisible to you. It comes with a form of a delay to you, but it is very invisible in form of that. But it is always there. Like the encryption patterns are always there. The encryptions are actually theoretically secure. So they are not insecure protocols. They are not insecure algorithms. They are mathematically secure protocols. Okay? Secure protocols. And you cannot break them by brute force attack or any form of mathematical form. But the problem comes that when these kind of implementations run in the microarchitecture, then the problem comes that because of the sharing of the hardware, there is certain kind of leakages. Okay. So today we will see certain forms of leakages that we see first of all in CPUs, and then we will extend it for high performance computing and typically for GPUs, GPU scenarios. So today the talk consists about exploiting leakages in CPU GPU microarchitectures. Okay. So first, giving a complete idea of what we are actually looking for and what I actually specialize is like given an embedded system, right? Embedded system can be in the form of several forms. It can be your mobile device, it can be your system, your laptop. It can be like even the bigger embedded systems. It's like the supercomputers that we have in this building. So now the idea is like how far can you, so ideally there are a number of users and they are running their computations on those embedded platforms, right? You are given the illusion that you are running alone on the server, but are you actually running your computations alone on the server? Not, right? You are sharing your computation along with several other users who are running their computation on the same server. So the effects can be in the form of like when I'm running my computation, I can observe certain parameters of my own computation run. Okay, that can be in the form of timing observation, that how less time or more time my computation might run while a neighboring computation is running. So that will give me an idea what exactly the neighboring computation is running. Okay, so say for example, I'm running computation and I'm running without any neighboring any neighboring no neighboring computation is running. I'm running that computation alone. So it might run in X amount of time, right? If there is a neighboring computation Y, it runs in X1 amount of time. If there is a neighboring computation Z, it runs in X2 amount of time. So if I can find out those Gaussians of those timing samples, and if there is a difference in those Gaussians, then it is clearly apparent what the other person is running, right? So this has nothing to do with how how the computation is written on the for the neighboring code. That it might be completely encrypted with the highest encryption standard and everything there, but still by looking at the shareability of the code, by looking at how the computation is running on the shared processor, you might be able to learn more information about the other process, right? So there are two basic forms of, so this has been studied over last decade, like timing channels came into picture. So there are two basic differences, different types of attacks that might be possible. So the left hand side part is called the non-invasive attacks, which is typically done over a network where you don't need a physical access of the device. You have timing observations of your computation run. You have performance counters of performance counter events of the run, and you can observe it over an internet connectivity on a network connectivity, and you can do whatever post processing that you need to do and find out the leakages from those. What the other form of attacks which are possible are known as invasive form of attack. Okay, so invasive means that you have the system at your end. So you have typically the mobile device at your hand, and you want to observe that how the performance is observing, and you want to observe it through high power like microscope, or you want to do it through an oscilloscope, like the power profile of the oscilloscope, or you want to do it through the electromagnetic wave calculation of your how your device is emitting. So typically, this is the two different ways how you can for your attack. So I generally deal with non-invasive form of attack, which is like over the network, where you can typically deal with the timing information of the computation, or you can deal with the performance counter of the performance counter events of those computation. Okay. So until this point is clear. Okay. So microarchitectural attacks, and why do they really matter, right? It might seem to you that this is like very far-fetched things, and why would a person even come up with something and do something like this? So the idea is that since the connectivity has gone up so much, and we have like systems from the known vendors only, right? We have systems of Intel. Probably this system is from Intel. Right? Most of the systems are from AMD. And there are processor families, processor generations. So generation after generation, the microarchitecture is evolving one after another. So there are basic concepts which are actually spanning over decades, like 40 years, 30 years, like that. So branch prediction, 30 years of architecture history. So like that, so because of this backward compatibility, the manufacturers does not really change the computer architecture every year or every 5 years. Okay, they improve the performance, they change the delta on top of the architecture based on how the how the benchmarks are behaving at that point of time, or do they need extra things on top of that, but not drastically changing the computer architecture at all, because that will curb the overall performance of the hardware. So in that case, microarchitectural attacks, if you can find out one flaw, that is probably applicable to all systems that are manufactured by that vendor, and it is operating at that point of time, right? So the first thing that actually made rake and havoc on the Intel stocks and Intel like good name was Spectre and Meltdown, right? It came around 2018-19, and it kind of broke the entire concept of this being a myth, the microarchitectural attacks being a myth. The underlying idea that it uses it is basically the branch prediction optimization, the branch prediction hardware, how you can actually use the branch prediction hardware to leak information and use that to break out in some part of illegal code, or break out the kernel address space layout randomization that we have in our system. So I'm not going details into each of them, because each of them can be one like textbook like material, right? One class of a course. Okay, but I'm just giving you overview why it became very important over the years. Then soon the security engineers came up with foreshadow. Then came cache out. Then came zombie load, reader, and fallout. These are different forms of attacks which are known as microarchitectural data sampling attacks. So earlier attacks were all control flow attacks, where you can find out the control flow of a program, control flow sequence of a program. So say, giving you an example, if a code is doing if statement or an else statement, that is a control flow decision. Okay? But even zombie load, riddle, fallout, this became microarchitectural data sampling attacks, which says that even the secret data can be leaked. Like even your data, like the password and this kind of information, can be leaked out in the open, because the buffers are working in a greedy fashion. They are working in a speculative manner. They are forwarding information instead of checking the validity of the instructions. Okay, so that is the reason why this came into picture. So this had a huge effect on Intel, and also like the first project that came out in the open and like discussed this in the open was Google Project Zero. Then came several advisories from all commodity vendors, and they had an advisory had to be issued based on this kind of microarchitectural attacks. And then came the best scientific cyber security paper that went for Spectre. That was in 2020. So given this history, let's move on to the abstraction of secure design. So now you have an idea that what microarchitectural security actually means. This is a immensely interesting field of research, and this is a very cutthroat field of research. But the abstraction of secure design can be at several levels. As you can understand, starting from device physics, from later from that from digital devices, then from over logic synthesis, microarchitecture, the ISA, basically the x86 ISA or like RISC-V or open source ISA that you can think of. Then comes the OS, VMM or hypervisor, what OS you are actually running, but depending on the security of that, the program or the language that you are actually based on, that your system is working on, the algorithm that you are working, and the problem or the application that we will be looking at. So all of this complete stack is responsible for the complete security of your application being running on the cloud server. So we have to think of the complete abstraction. Now, here in this particular talk, we will be talking briefly about the microarchitecture because we'll be moving from CPU to GPUs, and we'll be briefly talking about application, which one of the research scholars are here, Shubhi is here. So she will be giving you some example how a machine learning application can be mapped first into a CPU, what are the timing leakages from there, and then into a GPU, and what are the timing leakages in those microarchitectures. And you will see that in these two microarchitectures, the concept is different, so the leakages are also coming from different sources. And some of the cases, it is not even like very understandable. Okay. At the moment. Okay. Okay. So now coming to the hardware performance counter. So are you aware of hardware performance counter? Have you ever heard of this term? No, right? So these are special purpose registers which are there in our system, and these are actually counters. Counts what? Counts the events that your CPU is computing. Okay. So what are the events? Say the number of instructions it is executing, the number of cache behavior, like the cache misses that are there, the retired instructions, even the software-based events like the context switches, how many number of page faults are there, how many number of what else can I think of? Like all memory-based things that you can think of, like all architecture observations and a bit of OS observations that you can do over the hardware performance counters. Okay, so these store hardware and software-based events related to an execution of a program, and such as cache misses, return instruction, return branch instruction, and typically it is dependent on the ISA, on the instruction set architecture. There are various open source tools which are there for, these are for the CPU, these are called Perf tools, PAPI, OPROFI, Valgrind. There are several others. For GPU, for NVIDIA specific, we have Comptime and some NVIDIA specific extra things are there. So we will explain that. Command line Linux tools. This is not very difficult to observe. If you are running an executable in your system, if you run perf stat, it's actually very fun to see this. So perf stat and give an event name, whatever you want to see, and give an interval duration and an executable name. Run that, you will see the statistics of how the program is running. The primary objective of incorporating the performance counters was to find out the health of the device. How good is your system performing? Is it doing good on the benchmarks? Is it working like with the absolute numbers? So now I move into the GPU architecture, and I don't know whether time will permit, but I have two very good research papers which I wanted to discuss, but I don't know whether time will permit. But let's look at the first one first. So closely looking into the GPUs. So let's look at the GPU architecture first. Okay. So just looking at the diagram, it might look a bit scary, but it is not. Okay. Why? Because there are several components. Each of these components has a particular work to do. Okay. Let's look at one after another. Okay. This is a graphical processing computation, like one computation kernel. Okay, so there are going to be several graphical cores like that, and inside that there is a there are streaming multiprocessors which are SMs. Okay, there can be multiple SMs in a GPC. Okay. Now, particularly these SMs you can think of as a processing unit. Okay, like CPU you have cores, in SMs you have in GPUs you have streaming multiprocessors. Now, typically from the name you can understand this is multiprocessor. So there are multiple computations can be done on a single streaming multiprocessor. How? Typically, one streaming multiprocessor is broken down into there is a specific instruction cache which holds the instruction that is executing. There is a, I'm coming to the word, but before that, there are cores, there are load stored units, there are other special purpose units also. There is a shared L1 cache, and there is an L1 cache particularly for each streaming multiprocessor, which stores all the data and the instructions pertaining to the computation that it is running. And there is also a shared L2 cache, which is sitting outside and which is shared with all the SMs. Okay. Now, there is also a memory controller, which kind of decides what it will run. But there is a basic difference in the programming paradigms. Right? In the CPU, what happens? In the CPU, in one core, you can run one computation, whereas in the other core, you can run a completely different computation. Right? Also, in a single core, in presence of context switch of OS, you can actually run two processes and context switch them, which are running completely different workloads altogether. Right? It can be possible. In GPUs, these are structurally not going to work that well, because in GPUs, what will happen? This is a SIMT based processor. What that means? This is single instruction, multiple threads. So typically there are several data units that are there, and they are all executing one instruction. So say for example, you have a multiplication operation and you want to do a vector multiplication operation, right? So AI is equal to BI into CI and you want to do them all of them in parallel. What you can ask is that the instruction is a multiplication instruction, but you can feed BIs and CIs in parallel to all the warps in the simultaneous multi-threading paradigm. And then you can ask the entire thing to work in a single go. Right. So this is fundamentally different as how CPUs work. So the GPUs generally do not allow co-location of different processors on the same SI. Okay. Now going ahead, the GPU programming interface. Okay. So one application, this is specific to NVIDIA. So NVIDIA has typically the CUDA codes that you have some hands-on examples, I guess. So one CUDA application is first broken up into number of kernels, right? How many number of kernels are required out of that? Now, typically one kernel is now mapped into given the device, there is also a device driver, which actually maps the CUDA application into the hardware, right? So that actually breaks down into the number of threads, right? How you want to break down your computation into number of threads, do the SIMT computation in parallel, and then you get back the result in a way. So the concept is different. So since the requirement is different, the architecture is also different. In that case, we have L1s specific to the SMs, whereas there is a shared L2, which is there. So, okay. So going forward, there is a push towards sharing, because now since we don't have GPUs, I wouldn't say we don't have GPUs. I would say that okay. Now, since the cloud computation is becoming more and more popular, so now GPU cloud computation is also becoming more and more popular. In that context, if you kind of keep this paradigm, then a huge part of the processor is going to start, because maybe some computations are not so parallelized to actually use the entire part, to utilize the entire thread situation of the GPU. So in that case, sharing is nowadays much more promoted, but not in a very optimized way as CPU can do. Okay. Now the performance counters, as we were talking about CPU performance counters, equivalently the GPU performance counters. So there are typically performance counters connected to the memory. So device memory read, write, throughput, transaction. Global local shared memory load, store, throughput or transaction. L2 read, write, transaction. Device memory utilization. So these are typically the broad aspects which you can observe, by which you can observe the memory utilization in GPUs. On top of that, you have some instructions, the instruction profiling that you can also do through the GPU. Those are control flow, integer, floating point instruction, integer instruction executed, issued, executed instruction per cycle, issued load and store instructions, issue stall reasons, data request, execution dependency, texture, etc. So these are really fun things to look at, right? If you're interested in working with GPUs in future, go through the performance counter manual, see what kind of performance counter are allowed on your architecture. Because as I said earlier, the performance counters are specific to the, first of all, the architecture it had, like what kind of system you are seeing, and what vendor that is providing you the system, right? It might vary from vendor to vendor. Okay, so typically, but like on a overall basis, the performance counters observable in GPUs are much larger in number than in CPUs. Okay. Okay, so now having a brief comparison across CPU and GPU would be nice at this point, because this would give you an understanding basis on the security of how the security of the two systems are comparable. Okay, so in CPU, what we just discussed earlier, that the co-location was possible, right? Two cores were like two threads were able to run on the same core, and they could run very different applications, and they can possibly see each other's statistics by the relative effects of one another run. So that really is not possible in all scenarios in the
Yes. Start microphone. Microphone is off. Hey, camera is off. Camera is off.
I hope it is now visible and audible to the viewers online. Now we'll talk about some leakage vectors on the GPU. Okay, so typically the first API that leak information in GPUs would be the memory allocation API. So why it leaks information? Because whenever a computation asks for some memory to be reserved or reserved for its computation, it gets a chunk of memory reserved for it, right? But based on what kind of computation it is, right? So there will be the amount of the memory will vary. Okay, right? So what kind of computation is requested by the process, that actually decides that what amount of memory that would be reserved for that process. Okay, so this is a basic source of leakage in the GPUs. Okay, the second part is GPU performance counter. So of course, because it is observing the performance counters over all computations, though it is not as fine-grained as CPU, but still it will leak some information. The timing operations, of course, because the measuring the time of the memory allocation events or measuring the time of the computation itself will give you an idea that what kind of computation it is running. So now going ahead with the thread models. So there are three basic different type of thread models that might be possible. One is the as you know, the GPU has GPU specializes in the graphic rendering process in our systems. So one thread model that could be possible is to do a graphics to graphics thread allocation. So in that, the spy and the victim, so point. See the laser pointer. Okay. So here the victim is running one of the web browsers, and the spy is another OpenGL application, which is also one other graphics application, which is running on the GPU, and it is just observing the memory utilization, size, and time. Okay, so giving you a very simple example, let's say you are working with a web page and you want to open a website. Okay, you want to open a website. Now you want to log into a website. Okay, if you are already a user, like if you are already a registered user, it will open up the login page for you, the sign-in page for you, right? But if you are a new user, it will open a sign-up page for you, which is a more more elaborate process, right? So these two operations are different in terms of how much amount of memory is allocated for each of these two processes. So if it is a sign in, it might take one particular page. If it is a sign up, it might take up multiple pages. Okay. So if you just observe those kind of observation, you can create a clear distinction as to what the user is actually doing. Now imagine this, that you are doing it in a cloud server, you are somehow co-located and you are somehow able to observe this kind of information over the network, then you are actually able to see the data of somebody who is sitting just next to you and connected to the same cloud device without even without even tampering any device or without even looking at what is exactly happening. Okay, so the second threat model is CUDA cloud. So in both in these cases, both the victim and the spy is a CUDA app. They are both running on the GPU and they are observing the leakages over performance counters. This is another threat model. The third threat model is a graphics CUDA situation where the victim is one of the web browser situation. The victim is sitting in the web browser, whereas using the screen rendering observations, it is observing the CUDA application that is running on the GPU. And it is looking at the memory utilization and the performance counter of these applications. Okay, so these are the three viable threat models that could be possible on a GPU system. Now let's look at some actual experiments, and like you might think that these are all stories and this might not work in real life, but this is not, and this is really easy to observe if you have a monitored environment. Okay, so say for example, there are three cases. One is this Google, Amazon, and Facebook, and you are kind of so website fingerprinting is the first use case where both the spy in the victim is a web browser application, the graphics case, and then you can see that these are the memory allocation events over time. So x-axis is actually over time what is happening, and y-axis is the amount of pages that it is requesting, the memory that it is allocating in size KBs. So typically, Google, Amazon, and Facebook have a repeatable nature of these patterns over time. So this is just one incident, but if you look at the time series over time, this would be a repeatable nature of events that comes over and over again. And this can be used also as a template. So if you already have a template in hand, then you can already compare and see that, okay, this is this particular thing running. This is Amazon running. This is Facebook running something. Just giving you a small offshoot of this kind of work is something that helps us to find out whether you are using dark web or not, whether you are using Tor devices or you are using some websites which are actually prohibited or not. This kind of applications are used by cyber analytic teams to find out what kind of website you are actually using. So in that case, these fingerprints are not generally very easily fooled, and these are very repeatable nature. These have there was one work that we did with this kind of fingerprinting. With this, we observed the ransomware like footprints, and we kind of put like throttle the ransomware in a record time, like in very short amount of time before the ransomware was can wreak havoc in your system. So these are very powerful tools, and the website fingerprinting is one such technique. Okay, the next comes user activity tracking. Okay, so this is another example where say for example the user activity memory trace of a Bank of America website, and this is a sign-in application. This is a sign-in memory allocation event, and this is a open account memory allocation event, and the checking and saving everything can be distinguished. So typically, nobody will actually find importance in finding out what you are doing in Facebook or might be like that. But this kind of banking applications or like which are sensitive to human can be actually detrimental if you do this kind of user activity tracking. Okay, typically you can see different kind of behavior also, the signing in, the account page when it is opening, the open account, check and saving, and it is usually a time series sample. You can observe it one after another in time series steps. Okay, that's Facebook example. So in this case, the Facebook example memory allocation event, the Facebook sign in, and if you can actually see that these are user inputs. Okay. So typically 1, 2, 3, 4. So the time intervals it is waiting and the memory allocation event is dropping. So typically 1, 2, 3, 4, 5, 6, 7. So 7 bits of password probably. And then there is a bit of like keyboard interrupt observation, and then you can actually hack the password for anything. And this is just an example for Facebook, but can be applied to anything and everything, right? There is also an adjusted error along with that. So typically, statistical techniques works beautifully in that case. The standard deviation, Gaussian sampling, and these kind of things work very well. But there are also like there is also machine learning techniques nowadays which are getting used now to do this post processing more error free and with less samples. Okay, so these kinds of things are there, and for further reading I have been reading this material, rendered insecure GPU side channel attacks are practical. This was published in one of the top tier conferences in the world, the CCS 2018. It's a very beautiful paper, and the group of researchers come from a computer architecture background, so they describe architecture concepts really well. So if you're interested, you are free to go ahead and check out this paper. In the next section, Shubhi will be talking about some experiments that we have been doing on our side. But let me go ahead with the second finding, right? I hope you are enjoying this event. Okay. Okay, so now the second part of the thing, this is called leaky DNN. So stealing deep learning model secret with GPU context switching sites. Okay, so typically in the earlier abstraction, we were talking about several levels of system security, right? If you just look at the application level, like just keeping everything constant, if we just change the application across, there can be also application specific timing channels or leakages that is possible. So one application which is very common these days is the MLAS situation, where the machine learning as a service, deep neural networks, the convolution neural networks, and when they are getting like the image processing algorithms, when they run over the deep neural networks and then classification happens, and then ultimately you get the predictions that which classes happen. Though I'm not a expert, I'm not an expert of machine learning. Okay, Shubhi knows much more than that. I learned from her, but I'll talk about briefly about the ideas, overall ideas, because the security concepts are more or less. We try to extend the concepts from CPU to GPU, but they are not always extendable, as we saw earlier. In this particular paper, they asked certain research questions. The first thing, can the adversary infer DNN structural secret like layers and their hyperparameters by exploiting the GPU side channel? So can you learn all the hyperparameters, how many layers the DNN has, just by looking at how well or how badly the DNN is working and looking at the timing and the performance counter leakages from the GPU, right? This is just the problem statement. The previous work from this has were only able to see that the number of was only able to learn the number of neurons in the DNN's input layer from the GPU, but this work goes one step beyond that. Okay. Now, giving a very brief introduction about what neural network, how neural network looks like. The neural network typically consists of a set of nodes, the neurons and units, which are connected by links, and each link typically has a numeric weight. So this is an example of a deep feed-forward neural network. The bigger case for neural networks, the convolutional neural networks or deep neural networks, has multiple layers of convolution, max pooling, and finally gives out the entire neural network. So typically we will be concentrating on this particular applications in this part of our talk. Okay. Now in the cloud GPUs, how does this actually translate into cloud GPU cases? Now most deep learning models are used for training and running in the GPUs, and multiple users share the same GPU, which is co-located. So co-located in a sense that typically the essence would be given to different users, right? So typically the users are using the same architecture that is running in the GPU, but the data is varying across. correct? So in that, the user do not have the direct access to each other's work. So there is a basic isolation, but we want to break that isolation by looking at the leakages from the GPU architecture. Okay. Now, similar picture to what we saw earlier, that the kernels are getting mapped now into SMs, and then it is mapped into warps and threads, and eventually it gets processed, right? I'll go fast on this. Yes, from here. The GPU profile. What does GPU profiler do? So typically, GPU profiler is used by a GPU application for performance tuning, right? For this particular example, the NVIDIA profiler called CupTime has been used for observing the profiler statistics. So exploited, this is used for model seeding and created labeled training data set. So which is used for as an input, is used by as an input to the model, and by correlating the CupTime readings with the TensorFlow timelines, we can get the leakages working. Okay. Now, how does the adversary model look like? Just like the previous example, we also have an adversary modeling picture. The adversary model says that the spy CUDA application and the victim CUDA application are launched on the same GPU. That is a realistic assumption because it is a cloud-based service. Now, feasibly, the cloud-based service, multiple applications are sharing the same physical GPU. Spy uses CupTime readings associated with each kernel execution to infer operations run by the victims. So the spy is just observing the performance monitors observation through the CupTime utilization that is there with NVIDIA. Now, adversary has profile combination of layers and hyperparameters on the GPU. The goal here is to learn which layers and hyperparameters are chosen by the victim model. So typically, the adversary model is like this, just translating it into a figure. So this is the CUDA victim. It is running on the GPU. I'm trying to learn of the hyperparameters that the victim that the model is running. Okay. Now the CUDA spy is coming. It is reading the CupTime readings from the inference model. The profile layers and the hyperparameters are also being input to the inference model. Just by doing some post processing on the observations of the CupTime leakages, we can find out victims' DNA model structure. Okay. Now the TensorFlow scheduling. How is this done? Given a model, a machine learning platform, how it breaks up into certain stages is like there is a convolution, there is a ReLU, there is a bias and pooling and magma. These are the same specific operations that gets done one after another and over and over. Now, typically they get mapped into a NVIDIA CUDA DNA library, which has exact same like drivers for doing this particular operations. Okay, so they are like convolution forward, CUDA DNA active ReLU, bias forward, pooling max, gen. So these they are getting called based on the NVIDIA library that it has. And finally, this particular thing is getting run on the GPU. Correct? I will skip this because, okay, no, there is an interesting concept over here, which is called multi-process service. Okay. So now GPU scheduling. There can be a concept of GPU contention, which occurs when two GPU kernels are executed together, when they are fighting for the same resource in the cache memory. Okay. Now, two approaches to handle this contention is there. One is to interleave the kernel execution and context switch based on the time-based scheduler. Okay. The second concept is like kernels run concurrently and with the enabled CUDA enhancement, which is called multi-process service with the NPS enabled. Okay. In this world, probably the people have gone forward with NPS is equal to disabled. The assumption is also that the different DNN operation result in different context switching penalties, which is measurable by the spike in the half-time observations. Okay. So typically multi-process service can be visualized in this way, where there are A, B, C, three processes which request the GPU. There is a multi-process service and they are all working together and they are using the GPU. So this is MPS enabled. Whereas when MPS is disabled, this works in one another in the context switched fashion, right? After A, B comes, C comes, and like this. Okay. So MOSCONs, the model, I don't think I have time for this entire attack. Rather, it would be interesting to see the discussion that we have regarding the code and the timing of service that Shrubi will show. Okay. So I am. So if you are interested in the full like paper, you can go for this leaky DNA. The paper says stealing deep learning model secrets with GPU context with side channel. This is there are not many papers. Like in CPU, you have a lot of microarchitecture leakage papers. In GPU, there are not so many papers. So these are the two interesting papers of the few. And if you are interested, you can go ahead and read that. So thank you, and so we will carry forward with a small demonstration. Thanks.
So good afternoon, everyone. I'm Shubhi, a third year PhD student at CBS. And as Shalini has already given Professor Shalini has already given a brief background on GPUs and attacks on GPUs. So I'll be discussing about one of my works, which I presented recently in chess conference. And in that work, we exploited a timing leakage in PyTorch, but in CPUs. So now what we are exploring is how this leakage kind of works in case when the machine learning models are actually implemented on GPUs. So first, I'll be briefly discussing about the leakage which we found out in CPUs for the PyTorch library, and then I'll be discussing the result in GPUs as well. Okay. So we know that there are multiple machine learning frameworks available recently, and some of them are PyTorch, TensorFlow, JAX, and Mindspark. And what we try to look into is the security implications of these various frameworks. Like, are they secure towards various kind of attacks, like model stealing attacks or membership inference attacks? In this particular work, we actually looked into only PyTorch. And the reason we can clearly see from this pie chart is that PyTorch is the most used machine learning framework on this day. And this is from a statistic from June 2023, where 60% of the GitHub repositories were using PyTorch for training their machine learning models. I'll give a brief background on convolution neural networks. And so, like Dr. Shalini also already mentioned about this before, like what are convolution networks, but I mostly focus on the pooling function in these CNNs. So CNNs have these, we know, are consist of convolution layers and pooling functions, and finally the dense layers. But what happens exactly inside these pooling functions? So pooling functions are basically used to reduce the dimensions of the previous layer or the convolution layers for better computation. And there are various pooling functions that are available. So like the commonly known pooling functions are max pooling and average pool. So talking about the max pool function, what it does is, so let's say you see on the left side, we have a matrix of some numbers. So we have to reduce this matrix to a smaller size. So we take a certain window size, which is also called as the kernel size, that is 2 cross 2. And inside that kernel, we try to find out the maximum value. So if we see that you get the maximum value as 56, then in the second we see as 9 and 12 and 32. And we finally get a reduced vector in this case, or a reduced tensor in this case. So in this one, we actually exploit max pool, and that is why this brief introduction on this was required. So now we talk about the timing leakage in PyTorch. There's a spelling mistake. Okay, so let's say we have two convolution, one convolution network, a CNN network, and we give input to it an image of a horse. So let's say we are considering a CIFAR 10 data set, which is a very standard data set in machine learning. So we give it an image of a horse which belongs to a class CI, that is for horse class, and then we give it an image of a dog which belongs to some other class, that is CJ. Okay, and now we give these images and get the classification result. But also during this classification result, also calculate the time which it took to do this inference by the CNN model. And what we would expect in a general scenario is that because all the computations are same on these two images, the timing should also be similar. But what we actually observed was that these two timings were different. And then we name this difference as something called as class leakage. So the inference time for images of different classes is not similar here. And that is why we name this as class leakage. And now we find out that why do we observe this class leakage? So first we start by analyzing a time of analysis of the timing measurements and how we first formalize this leakage. So first we only saw this for like two single images, but what happens if we have like 10 classes in a CIFAR 10 dataset? How are we able to distinguish between different pairs of these images? So again, we have the same CNN network and we give this input, some image of class CI and get the timing results, and let's say it's TCIK. So we get multiple distributions. So let's say if we have 10 classes, so we have mentioned Z. So let's say we have Z classes. So we get Z distributions of timing distributions of different image classes. Now the objective is that let's say we have two distributions, timing distributions, TCI and TCJ. So how do we differentiate between, or are they, like, what we have to check is, are we able to differentiate between them just by looking at their distributions? So one method is to like just look at the distributions, and other is that we do something called as t-test. between the two distributions. So t-test basically compares the means of two groups to assess if they are significantly different. So we did this t-test between different pairs, so like TCI and TCJ. So if we had Z pairs, we basically had ZC2 a number of, if we had Z classes, then we had total of ZC2 pairs, and we applied t-test on each of these pairs. So finally, we say that we get this statistic, and for each pair of this TCI and TCJ, we report that if if the t statistic value or the modulus of t statistic value is greater than 4.5, then we can say that the two distributions are different. So now going on to the results of various CNNs and on different systems. So we actually performed this experiment for, first we took a very simple CNN of our own and did some different distinguishing experiment. Then we also took some standard CNNs, AlexNet, DenseNet, TresNet, and SqueezeNet, VGG19. So the pre-trained models of these networks are already available on PyTorch. So we took those. And what we observe in these plots is that if you see, like we first look into the first plot, so it is for Intel Xeon system, which is a server type system. And we see that the number of pairs, so the blue, the red line indicates the differentiator for CIFAR 10, which has 10 classes, and the blue lines, the blue bars are for the CIFAR 100 dataset. So on the red, we see that the number of distinguishable pairs out of 45 pairs is going above 40. It's around 40 to 43. That means that if we have a class, total number of classes as 10, and we have 45 pairs, then we are able to kind of distinguish majority of the pairs. And this kind of confirmed that there is a leakage in PyTorch because of certain reasons, which we'll discuss later. And this was observed across all the CNN networks, which we took into consideration. And this was observed in CIFAR 100 dataset as well, which has 100 classes and total of 4950 number of pairs. And the blue bars indicate that. So we also tested this on two different systems, Intel Xeon and Intel i7, to confirm that it exists on every kind of system we can test it on. And of course, we only tested on the CPUs right now, and we observe this here also. But the question comes in that, okay, we do observe a leakage, but what is the reason behind this leakage exactly? So we do a layer-wise timing analysis for this reason. So currently, we were looking at the timing value of the entire CNN network, like from start to end, we were looking at the complete timing value of the inference. But now what we can do is that we can break it down, the timing values, we can break it down to number of layers. So let's say the custom CNN model, which we took, had 20 layers. So we broke down the timing values to 20 layers and got the timing value of each of the layers. So like convolution, ReLU, operation, then convolution layer again. And finally, from the, and again, we did the same experiment of this t-test, but layer wise. So like if we take a class pair, let's say CI and CJ, then for CI and CJ, we compare the timing values of convolution layer, then the ReLU layers, and so on. And here we observe with this timing analysis that this leakage is actually caused by the max layer. So if you see in the plot that all other layers have like values closer to 25, 30, but or like even lesser, we have like values around 5 and 10. But the max pool layers, the two max pool layers which we had in our custom CNN model, show the highest leakage of across by distinguishing total number of 40 to 45 pairs in the model. So next we want to check whether this problem only or this leakage only exists in max pool, or is it also observed in other pooling as well. So we see that it's also observed in average pool, like it's not observed in average pool. So from that we figured out that there's something in the implementation of the max pool in PyTorch that is causing this. And now we try to understand what exactly caused it. So we noticed that inside PyTorch, there's a very simple branching statement operation, which is actually used to calculate the maximum value. And so like it calculates, it has an initial maximum value and it kind of gets the maximum value on the current, like if the current value is greater, then it stores the current maximum value. So I'll show you how, so the two instructions inside this if are only called in certain cases and not all the time. So we show this by some animation here. So let's say in this window one, we have this for input class X and for this 3x3 kernel size. We see that only like 5 times this assignment operation occurred, whereas in the second window, it happened 3 times. And for input class Y, it happened for 4 times in the first kernel, and in the second, it happened for two times. So in total, for input class X, we had 8 assignments, whereas for input class Y, we had 6 assignments, which are unequal, and therefore they caused a difference in the timing, which we observed. So this is, we now have found out the reason, and this is how it works in the CPUs. But then we also wanted to check how it works on GPUs. Like, does this branch prediction also causes problems in GPUs when machine learning models are implemented or the XCNN models are implemented there? So this is the results what we saw for the CPU, and this is what we saw for GPU. So in GPU, we see that there is no leakage as such from the max pool layer, whereas in CPUs we had a very huge leakage from the max pool layer. And from this, we found like we already know there are like huge architectural differences in CPU and GPU as has been discussed before as well. But the main reason here why we observe that the max pool is not leaking is because of a certain like a certain quality which in terms of how the CPUs and GPUs deal with branches is that CPUs have something called as branch prediction, where the branch predictors are used to predict branch results taken or not taken and proceeds with only one decision. And later, if the decision is incorrect, they flush the pipeline and go with the another branch. But in GPU, that does not happen. So they actually only like they go ahead with both the threads, like both the branches in parallel on different threads, and based on a masking bit, they decide which result they have to move forward. And therefore, because there is no difference, like both of them are executing parallelly, so there is no timing difference that we can observe here. So this is just one of the many differences that we observe between CPU and GPUs, but there's further exploration needed in this area. So to conclude, there are vast architectural differences between CPUs and GPUs, and that means that the attack methods devised for GPUs may not directly be applicable to GPUs. And this actually highlights the need for security research focused specifically on GPU architecture. Also, the security of GPUs have a additional significance in machine learning because machine learning has been used in various high performance computing tasks. And it's important to make machine learning models secure because of make them secure against privacy breaches as well as security breaches. So this is the paper which I had discussed before, the results for which I had discussed before in the CPU aspect. And this is the GitHub repo, and I'll go through a bit on the code on how we implement it on the CPU side and how the GPU side differs.
But in max pooling, there is a maximum operation. That is why there is a if condition. That is why there is branching involved. And in average pooling, there is no conditional operation.
Yeah.
So there is no branch operations.
Yeah.
That is why max pooling is showing the rules and average pooling is not.
Yeah, that is the reason.
Okay. And GPU already masks it.
GPU doesn't mask it. Basically, it executes both the branches together in parallel. So, like in CPU, only one, it will go ahead only with one decision. So, like if it takes, and if it realizes it was wrong, then it will flush the instructions and go ahead with the right decision. But in GPU, executes both parallelly.
Okay.
And then only goes ahead with the correct result. So there's no difference in timing there. Okay, so this is the repository I was talking about, which we have implemented for our work. But I will show a few snippets from this repository on how you can actually see for yourself how this CPU leakage can be observed, or like you get your own timing values. So, okay, so the first thing is that you implement a simple CNN network. So we have very simple CNN network with certain number of convolution and maximal layers, which we saw in the plot as well. Now we have like two pooling functions here. One is here, one function is here, and the other is here. And the thing, the timing values which we take are here. So here, this line actually mentions that we give input of certain class. So, and like any image from the CIFAR 10 data or CIFAR 100 data set, and we get the test out. So we actually want to measure the inference time of this particular operation. So for first, we like just apply this timing values just before and after this and collect it for various different number of classes. So this has been done for 10 classes of Zipartin dataset. And we save the timing values for 1,000, like 100 images of each of these classes. So 10 images of each of these classes to make it more generalized. And finally, we compare this using t-test. So this is how we can do it for the whole inference time. And we have also like chosen for different networks. So for custom CNN, you can choose also for different CNN networks. But the more important one is the layer-wise experiment which we did. And again, we define the layer, same layers here. But what we do this time is that before and after each layer, we give a timestamp counter. And then we kind of get the timing values for each of the layer. And again, perform the t-test for each of different classes. But now say for the time value saved in the layer-wise fashion. So is there any questions from the implementation side? So that is all from my side. Thank you.
Somebody is asking that can we get the GitHub link?
Yeah.
Online.
Yeah. Should I post?
Yeah.
Okay.
That's me. Finish session. Section.
No, not on chat, next person. Q&A, next person.
Where? Okay. Okay.
Can we get the question, the top.
Okay.
And the slides which we have. So we'll also share the slides.
Okay.
Thank you, Shubhi, for sharing your research insights, and thank you, ma'am, for such an insightful session. We would request you to come here and take this proper lesson. Thank you.
And it's been. So, review after
You can come back here.
and I said that the feedback form will be given.
Right.
Need by young.
Right now, we'll be taking the lunch.